connection doesn't die out here. Apparently my connection died out in the first discussion and led to some horrible things, but all right, let's go. So today's discussion is going to be on transfer functions and filters. And personally, I think this is one of the better topics in circuits. I think this is really where the material starts to get good. Thought all the time stuff was kind of boring, but you know, it is what it is. So, all right. Let's just do a quick recap of some of the things that have been going on in the past couple of lectures and on discussion on Monday. So you might remember from Monday's discussion that if we treated all of the voltages and currents in our circuit to be sinusoidal, this gave us a very special technique called phasors to analyze our circuit. And the real key here behind sinusoidal voltages and currents were that linear circuits, and a linear circuit is just a circuit consisting of resistors, capacitors, and inductors. They don't change the frequency of a sinusoid. So if you have a sinusoidal voltage or frequency omega, this means that every voltage and current in that circuit is going to have that frequency of omega because it's linear. So this is really what lets us use phasor analysis. And when using phasors, we're essentially just ignoring all notion of time. We're just only going to look at frequency. So the way we do this, you might recall, is if you have some sinusoidal voltage, V of t is equal to A cosine of omega t plus phi, then we treat this as a phasor. Capital V is equal to A, which is the magnitude of the time voltage, e to the j phi, which is the phase of the sinusoidal voltage. And again, notice that phasors don't depend on time. And this kind of let us write our entire circuit in the phasor domain using impedances. And impedances are the, I guess, complex analog or the frequency analog of resistors. So you could treat resistors, capacitors, inductors all as impedances, with impedances R, 1 over j omega c, and j omega L. And they all behave the exact same way as resistors. So impedances in series behave like resistors in series, and impedances in parallel also behave like resistors in parallel. And if you did the homework, I think one of the questions talks about why KVL and KCL also work for phasors and impedances. So yeah, any questions? I know I've said a lot in the past minute, but any questions about, I guess, phasors and impedances, or really just what we've been doing so far? Okay, we don't have any questions. Let's just do a quick recap example where if we're given a circuit in the time domain, let's say we have some sinusoidal voltage, some resistor, and a capacitor, then we can transform everything into the phasor domain. So whenever you want to work with frequency, the first thing you do is transform everything into phasors. And the sinusoidal voltages are all going to become their phasor equivalents. And then all the resistors, capacitors, and maybe inductors will become R's, 1 over j omega c's, and j omega L's. So we're just converting everything into the nice phasor domain where we don't think about time. And then we solve for everything we want to solve for. In this case, if we want to find V out, we solve for V out phasor, and then we convert that back into time. And to give an example, if V out was equal to 2e to the j pi over 4, then in the time world, V out of t is just going to be equal to the magnitude 2 cosine of omega t plus pi over 4. So it's really just another way to represent a sinusoid without thinking about time. So any questions about what's been going on so far? Okay, if we don't have any questions, let's just briefly talk about the plan for today, kind of the ideas we're going to be looking at today. So for today's discussion, we're mainly interested in how these circuits involving resistors and capacitors and sinusoidal voltages, behave for circuits or behave for inputs of multiple frequencies or different frequencies. So we want to take a look at a range of frequencies. Like, for example, what if we have a very low frequency signal, or what if you have a very high frequency signal? So this is kind of the ideas we're going to be looking at today. Instead of thinking about a single fixed frequency, we want to look at a large range of frequencies and see how it behaves in general. And the transfer function, which is this ratio of the phasors V out and V in, is really what's going to let us do this. And the transfer function is a function that maps a frequency omega to a complex number, which depends on omega. So it's a function. And I think if we look at more examples in the discussion, this might be a little bit more clear. So again, it takes frequencies omega and outputs a complex scalar. If you took 16a, you might remember gain as V out over V in. And this is really just the frequency analog of gain. And lastly, transfer functions are really useful because they help us design a bunch of filters that can block out certain frequencies. So, for example, let's just say we have some frequency, I don't know, 20 kilohertz that's really annoying. And we want to block it out. Then we can design H of 20 kilohertz to be equal to 0. So it's just going to block out everything at 20 kilohertz. That's kind of the idea, while letting other frequencies through. And again, I think this part of the material is a lot more cool than the other parts because there's so many applications in things like audio engineering, Wi-Fi, and even computer graphics. Like if you think about like how Photoshop works, like filters are really the key behind sharpening and blurring images. So if you take any later classes on computer graphics or computer vision, filters are a really key idea there as well. So any questions about the overall plan for today? Right. If we don't have any questions, let's kind of take a look at the discussion worksheet for today. I've mainly gone over the meat of what's in the first page, so let's take a look at the second question, which is on circuit filters. And here we just have a simple RC circuit. Notice how the capacitor and resistor are kind of switched, but you can still analyze this circuit. And we're going to assume there's some sinusoidal input V in of t. So I'm going to give everyone a minute to work on this. And let's see. The main idea here is we want to find what the transfer function h of omega is. Since we know h of omega is equal to V out phasor over V in phasor. So I'd recommend you convert everything into the phasor domain and then work from there. All right, hopefully people had a chance to take a look at the first problem. And first thing I would do whenever looking at these phasor problems is to just convert everything into the phasor domain. So voltage V in becomes phasor capital V in, we have voltage capital V out. Shut up my timer over here. All right. And capacitor becomes 1 over j omega c, and the resistor remains at R. So this is our circuit in the phasor domain. And then you might remember the voltage divider formula, that V out is equal to ZR all over ZR plus CC. And we can again use voltage dividers because impedances behave the same way as resistors. So plugging in for all the values, we're going to get R over R plus 1 over j omega c times, whoops, I forgot a V in here. V in, and then this tells us that h of omega, which is equal to V out over V in, is just equal to R all over R plus 1 over j omega c. And a helpful trick is to just multiply the numerator and denominator by j omega c, just because working with fractions is oftentimes really annoying. This gives us the transfer function j omega rc all over j omega rc plus 1. So, any questions about the first part? Okay.
Wait, sorry, Tejan, what happened to the Vn that you were multiplying by?
Yeah, so I wrote V out equals this ratio times V in. And remember how
Oh,
h of
yeah,
omega was
sorry.
defined as V out over V in, so I just divided by V in.
Yeah, that makes sense, thanks.
Yeah, for sure. So well, there's only 17 of us here, but we can still use breakout rooms kind of just to work together. So I'm going to split everyone up into breakout rooms, and we'll hopefully, you guys can take a look at parts B and C. And the ideas here are, what are the magnitude and phase of the transfer function? And one hint I'll give you is that h of omega is a complex number. Meaning, the magnitude of h of omega is just the magnitude of the numerator over the magnitude of the denominator. And the phase of h of omega is the difference of the two phases. So take a look at parts B and C. Let's put everyone up into breakout rooms. And in the meantime, I'll also just jump around to see if anyone needs any help. So if you have any questions before entering the breakout rooms, also feel free to ask.
That's true.
Okay, hopefully people got a chance to look at
2050.
at least part B. Wait for people to come back, but I think I'll start out by just sketching what these numbers would look like on the complex plane. So j omega RC is a purely imaginary number. So it'll look something like this. And then 1 plus j omega RC will be a vector. Is everyone back now? Oh, looks like everyone's back. Okay, so to compute the magnitude and phase of these complex numbers, again, we just take the magnitude of the numerator divided by the magnitude of the denominator. So the magnitude of j omega RC, since it's purely imaginary, we can just say that's equal to j omega RC, omega RC. You might recall that the magnitude of a complex number is just the real part squared plus the imaginary part squared, all square rooted. And then the magnitude of 1 plus j omega RC, let's take the real part squared plus the imaginary part squared. And that should give us our magnitude. To compute the phase is just the angle of the complex number. So if we look at j omega RC, it's pointing just straight up. It's just a purely imaginary number. So its phase is going to be pi over 2. And then the phase of 1 plus j omega RC. You know, a lot of people in the breakout rooms have this question of how do I do this? And the phase, since it's just the angle of the complex number from 0, this is going to be the arctangent of omega RC all over 1, since the vertical height is omega RC and the horizontal width is just 1. These are just some triangle properties from trig. All right, so did anyone have any questions about all of this?
Damn. That looked painful.
All right. Were people able to start looking at part C or not? Let's just do a
No, not really.
poll. Not really? All right. Do you want some time to work on part C then? Or do you want to just...
Yeah, sure. Like a minute?
Yeah, I can give everyone a minute to just take a look at part C and how all this works. Is here though. Just take the previous results and kind of apply what happens. hopefully you all got a chance to take a good look at the question. And now let's take a look at how to actually solve it. So we just need to take the magnitude and phase from the previous parts and analyze what happens at very small values of omega and very large values of omega. So for smaller values of omega, you might notice that omega RC is really small. 1 plus omega RC squared is going to approach 1. So this is going to be approximately equal to 0 over 1, meaning the magnitude is going to go to 0. The magnitude at infinity, on the other hand, omega RC is going to be really large. The omega RC here is going to be much larger than 1. So we can treat this very close to omega RC all over the square root of omega RC squared, which is just omega RC. And that's going to go to 1. And then for the phase of the complex number, you might see that the arctan of 0 is 0. So really pi over 2 minus 0 approaches pi over 2. And then lastly, for the phase at infinity, the arctan of something really, really large, the arctan as omega goes to infinity will be pi over 2. These are just some properties from trig. So we're going to get pi over 2 minus pi over 2, and the phase is going to approach 0. So any questions so far in the math of what we've done? And now let's look at the last part here. So why does this behave like a high pass filter? Any ideas? If you have any ideas, just type them out in the chat. Low frequencies get sent to 0. Yeah, that's definitely a good idea. And yeah, high frequencies are let in. And again, I think the way we think about this is h of omega is equal to v out over v in. So if h of 0 or h of something very small gets sent to 0, then if this is approximately 0, this tells us that v out is equal to 0. On the other hand, if the magnitude is very close to 1, then this tells us that v out is approximately v in. So
Yeah, stop. I don't know because I feel
I think this should help with the understanding. And if you want some intuition on what the phase means, the phase is just kind of this delay. So phase tells us how much delay we have in our circuit. I think that's about as much intuition you need about phase. Magnitude is the real weight of things. Phase is just a delay. So, all right. Part D, we have a Jupyter notebook for this. And let's see if it's actually possible for me to share my screen here and go over this together. All right. So Zoom is so difficult. How do I see the chat? Are people able to see the screen share?
Yeah, we can see.
All right, for sure. So what we're doing here is we're just taking the expressions for magnitude and phase that we've kind of derived in the previous, I guess, question or part. And we're just plotting the magnitude of the transfer function over all frequencies omega now, just to kind of see this behavior of low and high pass behavior. And a couple of things to note here. We're going to plot on a log scale, and I think the reason why we do this will be more clear on Monday when you actually learn how to plot these by hand. And the log scale really lets you, I guess, add these plots together when you have much more complicated transfer functions. And also just because frequencies are stretching such a wide range, like you have frequencies from like 20 hertz, which the average human can hear, all the way up to like 20 kilohertz. We like to think of these over long ranges of, I guess, like magnitudes of 10, just because of the way human hearing works. So you might notice that for very low frequencies, the magnitude of h of omega is very small. 10 to the third is very small. And again, the y-axis, the magnitude of h of omega is also on a log scale. If you haven't seen log scale before, it might be a bit hard to understand the first time, but it really is just 10 to the 1, 10 to the 0, 10 to the minus 1, so it just goes in powers of 10. So as we increase our frequency, the magnitude of the plot increases until around 10 to the 3, at which it starts to saturate at around 1, which is 10 to the 0. So any questions about what's going on in the magnitude plot? Okay. And 10 to the 3 here is a very important frequency. I think it's, in lecture, they called it the cutoff or corner frequency. And it really is where things start beginning to change in the plot. So you might see how this plot here is increasing with a slope of 1 on a log scale, but then it suddenly stops. And that's because this frequency here is called a cutoff frequency. And we'll investigate more into the meaning of this in the later half of the discussion and on Monday. And then the phase plot, if you take a look at it, remember how for small frequencies, we said that the phase was close to 90, as we kind of see here, and it starts dropping off slowly but surely. And again, at around 10 to the third, notice how the phase here is 45 degrees. And again, this is a really important point because this is where the plot begins to change, where for frequencies smaller than 10 to the third, notice how the phase is really large, whereas for frequencies much greater than 10 to the third, the phase is really small, close to 0. So it's kind of a high level intuition we want you to get out of these plots. So any questions as a whole about the plots here? Okay, if we don't have any questions, let's move on to the second half of the discussion. And the second half will introduce the very basics of how to start plotting these transfer functions. And we really want to know how to plot these transfer functions just to get a general idea of how to plot these without plugging them into a computer all the time. So actually, looks like we're doing pretty good on time. So I'm actually going to go over part E as well. I think I didn't have time to do this in my 10 a.m. discussion, but I have time to do it here. So I'm going to give everyone, let's say, a minute and a half to just take a look at this. And if you have any questions in the meantime, feel free to ask as well. We're just taking a look at a sinusoidal input now and try to understand how the transfer function plays a behavior in it. All right. Let's take a look at this together. I think the most important thing to remember is that our transfer function h of omega is j omega rc all over 1 plus j omega rc. And that rc, which is really our critical value here, is equal to 1 kilo ohm, which is 10 to the third, times 1 microfarad, which is 10 to the minus 6. So it's equal to 10 to the minus 3. So plugging in for RC, get the following. And I'm only going to take a look at part 1. I think the techniques generalize pretty well. So what we want to do is we have this sinusoidal voltage with frequency 1000. So we can identify the frequency of 1000. And first thing to do is to convert this into a phasor. So 4 cosine of 1000t plus pi over 3 can be represented as the phasor 4e to the j pi over 3. All I did here was take the 4 and the pi over 3. And then we can plug in our transfer function at the value 1000. And you might notice that this is j times 1000 times 10 to the minus 3 all over 1 plus 1000 times 10 to the minus 3. 1000 is really 10 to the 3, so these all cancel out, and we end up with j plus 1 over j. And the last thing we need to do is to say that V out is equal to h of 1000 times V in. And that means we need to multiply these two complex numbers. And multiplying this number, which is in rectangular form, with a number in polar form might be a bit difficult. So what you need to do is you need to convert this complex number, j over 1 plus j, into polar form. And the way we're going to do this is we're going to convert the numerator to polar form. So you might recall that j is equal to e to the j pi over 2. If you remember anything from this section on frequency and filters, this is the most important fact to remember. So we have e to the j pi over 2. And then we want to convert 1 plus j into polar form. And to do this,
1.
z is equal to 1 plus j. The magnitude of z is going to be equal to the square root of 2. And then the phase is going to be equal to, we plot this on the complex plane, it's going to be equal to pi over 4. since the arctan of 1 is equal to pi over 4. So this tells us that 1 plus j is equal to the square root of 2 e to the j pi over 4. And then to divide two complex numbers in polar form, we just divide their magnitudes and subtract their phases. So it's over here. This is going to be equal to 1 over square root of 2 e to the j. We're going to subtract pi over 2 and pi over 4. So 1 over square root of 2 e to the j pi over 4. And last thing to do is just to multiply this phasor here, or sorry, this transfer function here by this phasor here. So and again, multiplying numbers in polar form is really easy compared to rectangular form, which is why we wanted to do this in the first place. So we multiply their magnitudes, which is 2 square root of 2, and then we add their phases. So we add pi over 3 and pi over 4 to get e to the j 7 pi over 12. So I know I went through this a little quickly, but any questions about the whole process of what went on here?
Can you just go through one more time how you got the angle of z, with 1 plus j, z equals,
Yeah.
Yeah.
So this is the arctangent of 1 over 1, right? If you like, maybe draw it out.
The imaginary over the real.
Yeah.
Okay, yeah, got it. Yeah, thanks.
Okay. And yeah, so once we get that, we can just plug it in and multiply the two. All right. Anyone else have any barging questions? Okay, if you don't have any other questions, I think doing it for the other two parts are the exact same. And there's a neat trick for 5 volts, which is a DC voltage. And I encourage you to work on this on your own and try to figure out what the trick is. I can assure you this is sinusoidal with a certain frequency. All right, so.
What the fuck is that?
Yeah, I agree.
Oh.
I think we'll go over it in slide form, which is a bit less intimidating. So any transfer function, really, the example we had earlier was much simpler. It was something of the form j omega rc all over 1 plus j omega rc. But let's say we added a couple of other terms. I don't know, let's add a 1 plus j omega r over L over j omega L over R, something like that. And then let's add a 1 plus j times c all over 1 plus j times LC. It really doesn't matter what these are, but I think the idea here is that any transfer function, no matter how complicated it gets, this is nasty and awfully complicated, can be factored into a bunch of products of 1 plus j omega over something, and j omega to the something power. So the reason we can do this is the fundamental theorem of algebra, which says that any nth degree polynomial has n complex roots. So notice how this is a polynomial that is of degree n, and we can just factor it into all of its roots. So this is where this factorization comes from. And these denominator omegas here are all going to be constants, but we're going to call those the zeros and poles. And zeros and poles are really important and key to plotting these Bode plots, which is why we are spending some time today to really dive in and understand what they mean. So these are really important for plotting. So if we have a transfer function of the form 1 plus j omega over 50 all over 1 plus j omega over 100 times 1 plus j omega over 5, literally like pattern matching to what we have in this form over here, we notice that there's a pole here at 50, or a 0 here at 50, and a pole at 100, and then a pole at 5. So these are just zeros and poles by definition, really. And just to give more detail to this, if I were to add another j omega here, we would also have a pole, a 0, at omega equal to 0. So any questions about poles and zeros? I know it's a new concept, so it might take some time to digest. But
so what is it like? What does this mean graphically? What is like? How do we show what a pole is and what a zero is? So how does it help us?
Yeah. So if you remember from our, sorry, this is the wrong slide. From our transfer function example, I'm going to go to the 10 a.m. one because I drew this in the 10 a.m. one, but our transfer function was something of the form 1 over, it was like j omega times 10 to the minus 3 all over 1 plus j omega times 10 to the minus 3. Or really, j omega divided by 10 to the 3. So this tells us that we have a pole at 10 to the 3. And notice how I mentioned earlier in the discussion, 10 to the 3 is where things start to change. That's the key intuition that you need to get for now.
Okay.
On Monday, we're going to go over like how each pole and zero plot actually works and how to add these plots together. But that's the key idea in intuition. So the fact that you can break it up into all these products and you can identify the zeros and poles. And zeros and poles, as Bongi asked earlier, is really where things just begin to change. Where things start to change. So I'm just going to go over one example here. I think the rest of these you can definitely take a look at on your own time. I don't think we're going to ask too much of this on the homework, but it's very important to understand Monday's discussion. So definitely take some time on your own to really understand and internalize the meaning of poles and zeros. So we already saw this one in the slides. So we're going to take a look at this specific example over here, where we have 20 plus j omega times 40 all over 1 plus j omega times 10 squared. So to write this in rational transfer function form, we always want to write this as like 1 plus j omega over omega z all over 1 plus j omega over omega p. Some products. So we want to make this coefficient 20 a 1. So first thing you do is factor out a 20. And then we're almost there, but we're not quite there because notice how all of these frequencies are divided by their pole or zero frequency. But here it's multiplied. So you just need to massage the terms to realize that j omega times 2 is the same thing as j omega divided by 1/2 or 0.5. So you can write this as 20 times 1 plus j omega over 0.5 all over 1 plus j omega, and then multiplying by 10 is the same thing as dividing by 0.1. And since we have a squared, this is going to appear twice. So the final conclusion here is that we have a 0 at 0.5 and then 2 poles, sometimes called a double pole, at omega equals 0.1. And again, that's because of this squared term. We can just like break out this 1 plus j omega over omega p squared as two like products. So any questions about poles and zeros? All right, it is 12 o'clock. Luckily, I got to the end of the discussion on the recording. And if you have any questions, definitely feel free to stick around and ask. And I think to give a glimpse of what's to come, on Monday, we'll take a bunch of these transfer functions and you'll break them up into poles and zeros and learn how to plot these. So that's the overall plan for Monday.
Thanks, Tejan.
All right. Thanks so much for coming, and see you all next Wednesday.